tutorial questions, and I think there were 2 questions that we have not solved yet. So I think I want us to do those, and then we conclude our class. All right. So the questions left are regarding the drawing of some ladder diagram. Okay, let me just share my screen so you can see where the questions are. Okay, so we were looking at these questions, and I think question number 3, we did not solve question number 3. So let's start by question number 3 today, and then we conclude with the last question as well. Then I think the tutorial will have been covered adequately. All right, so now I think you have attempted these questions. I hope you've attempted these questions yourself. It states that Vivo Kenya has hired you as one of its engineers. Your first assignment is to write a program to control a pressure relieving solenoid valve in a gas processing system. Okay, so a pair of high pressure control switches signals the PLC when to open the solenoid valve. One telling the PLC to open the valve after a 3-second time delay, and the other called the high switch with a higher trip setting, telling the PLC to open the valve immediately. A push button switch serves as a manual override to open the solenoid valve immediately when pressed. In all the cases, the solenoid vent valve will remain open until pressure falls below the setting of a low pressure gas switch. Okay, and then there's the operating statuses of these switches. Okay, immediately now, let me just see. So there's the override push button, which comes connected as a normally open button. The low gas pressure comes as a normally closed button. The high gas pressure is normally closed, and the high gas pressure is normally open. Okay. So as usual, remember where we had said that the best way is usually to list the inputs and the outputs whenever given such a problem. So you need to have a set of inputs and list them. Now, here they are actually listed here. There is the override push button. So this is an input. I don't want to write it again. This is revision. You already know. So this is an input. So remember, you'll have to give it a name or and an address or something. The low gas pressure switch, because it's a switch, it's also an input. The high gas pressure switch is an input as well. And the high gas pressure, that's also an input. So clearly there are about 4 inputs there. The output, in all cases, the solenoid vent valve will remain open. Okay, so they are supposed to open the solenoid valve. So the output clearly is the solenoid valve. That is the one that's being controlled by the different switches. And I've also seen here, let me just check again. Yes, the one of the high pressure switches is supposed to open the valve after a 3-second time delay. So we also have a timer. So remember, a timer is an output instruction. So you have a timer as well. And it is supposed to open after a 3-second time delay. So you'll need an on delay timer, so that when it's activated, it counts to 3, and then you obtain your output. So the on delay timer also exists there as well. Okay, so you have the inputs, you have the outputs, and then you have the timer that you need. So then you can just draw the ladder diagram. So the idea here is we are told that the valve is opened by 4 different switches. That's where we have to remember, because there's a pair of high pressure control switches. This guy is here. There's a pair. So one telling the PLC to open the valve after a 3-second time delay, and the other called the high will with a higher trip setting telling the PLC to open the valve immediately. So therefore, they are listed here. So this one is the high gas pressure, the one that's connected to the timer. The high requires an immediate opening, so it also affects the opening of the valve. The override switch affects the opening of the valve. Otherwise, if the pressure is at below a certain, I think 10 psi, then that guy, number 4, then closes the valve. So it's only the low gas pressure switch that is responsible for closing the valve. So the override is supposed to open the pressure valve. The high gas pressure is supposed to open the pressure valve. The high gas pressure is also supposed to open the solenoid valve. And lastly, the low gas pressure is supposed to close it, meaning that there's not much pressure, so the valve can be closed. So the way I see this, there are, how do I put this? These conditions are very important. So this is open when pressed and closed, open when unpressed and closed when pressed. It's an override push button. It's already in the normally open position. So that's a physical device. So how are we going to connect the virtual device? The virtual device, it's an override. So it's supposed to be pressed. When it's closed, it closes when pressed. So the virtual device should also be normally open. The low gas pressure is in the normally closed position. That's the physical device. The condition is that it's closed when the pressure is less than 10 psi. So this is the point where it's supposed to open. So it's closed. The current position when it comes is such that it is closed when the pressure is less than 10 psi. And this is what we use to open the pressure valve. To close the pressure valve, because it's open when pressure exceeds 10 psi. So this should also be a normally open contact, because you already have a logic 1 coming through. The high gas pressure is normally closed. It's closed when the pressure is less than 10 psi and open when the pressure exceeds 30 psi. So this one, because it's supposed to be opening it's supposed to open the solenoid valve when the pressure exceeds 30 psi. That's why it's called high gas pressure. So when the pressure exceeds 30 psi, it's supposed to open the solenoid valve. Open the solenoid valve. That is when the pressure exceeds 30 psi. But it comes connected in a normally closed contact. It comes as a normally closed contact. But we want it to open. So it's closed when the pressure is 30 ps, is less than. And it is open when the pressure exceeds 30 psi. Okay. So it means we need to operate it in the open position. So therefore, this should be normally closed, because it comes as we are going to draw it and see. High gas pressure is a normally open, and it's supposed to be closed when the pressure exceeds 40 psi. Closed, then this should also be normally open, so that when I close the gas, the switch, It provides a logic 1, and then the valve opens. Okay. Let's see. I don't know where I can draw this. Let me draw it somewhere here where we can. Okay, so now we have to draw the ladder diagram and see if it works. Okay, let me see if I can draw this properly. I used to use a function here. I'm not sure if it works. Yeah. So the first thing that we need to draw is to look at this condition here. I think this is the key thing to figure out. You have a solenoid valve, which is an output. We need to open it. That solenoid valve is, let's assume it needs to be closed with an override push button. It also needs to be closed with a high gas pressure, but that high gas pressure goes through a delay and also the high gas pressure. Good. So there are three conditions that can close the solenoid valve, open the solenoid valve. One is the override, the other one is the high pressure, and the other one is the high pressure switches. So if I have a solenoid valve here, so this is my solenoid valve. It's opened by three main ways. One, we had said it's opened by the override push button. So somebody just presses the override push button and it's opening. And remember, the override push button comes connected as a normally open. So that means we are also putting it as a normally open, because the way it comes connected here is that it is already it's in the normally open position. So let me draw it properly. So you have a push button that comes already in the normally open position, like that. So this is the override push button. So that when you engage it, it provides a logic 1 to the virtual contact, and then that transfers the output there. The other condition is the high gas pressure. But the high gas pressure cannot put, so it could be if you have an override. If I have an override, that's a condition, sorry. If I have an override, then you can infect the solenoid valve. Alternatively, the other way to open the valve is when there is a high gas pressure. But we are required that the high gas pressure operates in such a way that it goes through a timer, because it's supposed to open after 3 seconds. So the other condition is the high gas pressure, but the high gas pressure has to go through a timer. So therefore, we can take control of, or we can consider that by having a contact here, because this is now OR. That's another way of opening the valve, is through the high pressure switch. But the high pressure switch has to go through a timer. So therefore, it has to go through a timer. So it means that the real action here will be from a timer. Let me just call it timer 1, done bit, because it's the done bit of that timer that will activate that. The other one is the high pressure switch. the high pressure switch. So the high pressure switch should also be connected here as an alternative. So this is another option, but this is the high pressure switch. So we have three conditions. The override can open the solenoid valve, the down bit of the timer, because that is the high pressure switch going through the down bit of the timer. Activating the down bit, and then the high pressure switch, which again opens the valve immediately. Then it's indicated here that we are supposed to have a low gas pressure that's normally closed. And it is closed when the pressure is less than 10 psi. So for conditions where the pressure is less than 10 psi, it's supposed to now close the valve. So if these ones were responsible for opening the valve, the three conditions, then these condition is responsible for, and it's supposed to be what contact is. It's a normally open contact. Is responsible for closing. So remember what I have done here. The best way to do this is we can say the three conditions, the override, the high pressure switch, and the high pressure switch are responsible for opening the solenoid valve. This is the solenoid valve. So those three conditions can open the solenoid valve. Then the low pressure, this is the low pressure switch, is responsible for closing it. Okay? So the reason why I'm putting the large conditions here is that one condition, it's supposed to hold on to this one conditions to latch onto the opening condition until the low pressure valve unlatches it. Okay? That's the best way to implement that. But please remember, the timer down bit we have not included, so we can include the timer down bit as well, because the timer down bit is activated by a high pressure switch. So you have a timer there, which has a preset value, I think, of 3 seconds. So usually it's connected to an enable there, and then we have a down bit there, something like that. So this is timer on delay. But now, let me see. We had said that this is the high pressure switch. High pressure. The high pressure switch. Let me go back and check if everything is fine. The high pressure switch that activates the timer is closed when the pressure is less than 30 psi and open. So it comes as a normally closed contact. So this guy here comes as a normally closed contact. Okay? I want us to understand something here. So this is a normally closed contact. Okay? But the condition here is that it is supposed to open. Remember, it's supposed to be open when the pressure exceeds 30 psi. So it means that when the pressure exceeds 30 psi, you're supposed to open this. You're supposed to, like, it breaks the contact or it trips. It trips. What we always say in electricity, it trips. So if it trips, then it will be providing a logic 0. But we have to activate the timer. And to activate the timer, we need a logic 1. So if this guy, if there's a high pressure exceeding 30 psi, there's a high pressure that exceeds 30 per square inch, what happens is the switch is supposed to trip or break contact, meaning it will be providing a logic 0. But the timer is activated with a logic 1. So therefore, this has to be a normally closed contact. This has to be a normally closed contact. So that when the pressure switch, the high pressure switch trips, or provides a logic 0 or breaks a contact, then we can negate that using the normally closed contact, so that we have a logic 1 that then activates the timer. The timer counts to 3, and then the done bit now is responsible for now opening the solenoid valve. So that works like that. Let me check the low pressure switch. The low pressure switch is closed when the pressure is less. So it should be closed when the pressure is less. So you can close it. So it's a normally open contact. So this one makes sense. This is a normally open contact like that. So this is normally open. So what we are going to do is, it is closed when the pressure is less than. So this, for this case, when the pressure is less than 10 psi, you close it. So when you close it, it provides a logic 1, which then unlatches, so that now the valve is closed. Yeah, so this condition is fine. And of course, the rest remains. So I think this is a solution that can provide can solve the problem as asked. So I can remove this, just conditions. Yes. So I don't know if there's any question up to this point. You can please ask. Let me also check if there's any comments on the chat, just to make sure that we're on board. We're only having these 2 questions to solve, and then we are done. Probably just brief you on a few things, and then that would be the end. Anyway, so I hope this is clear, and I hope you've also attempted it. My idea usually is, I don't think, and I believe there is another way that you can solve this. Now, you realize that there is no one specific solution to these application problems. As long as you stay within the rules of the PLCs and drawing a ladder diagram, you can come up with a different variation of this solution, but it still works. The idea is you have a solution that works, and works within the limits of the PLC parameters. So, like in this case, somebody might decide that they're not going to, you see, typically we would latch the circuit, but now you can see the conditions that we have here and how many they are. So it's very difficult, and we don't have a normally closed contact or a stop push button. So we can't latch it the normal way. It's difficult for us to latch it in the conventional way. Remember, we talked about the 2 different types of latches. So I believe this kind of latching is more appropriate for this case, because you have 3 conditions that opens the valve and only 1 condition that closes the valve. So you can connect in this manner, and then of course you have a timer that is involved as well. So this should be sufficient. All right, now the last question. Let me see. I don't know. Okay, go ahead. Mhm, mhm. Yeah. If you decide to use the set and reset latching instead of this. No, but then let's not confuse 2 things here. The set and reset instructions are latching instructions. Do we agree? So the set and reset are simply instructions within the latching. So I cannot penalize you for using it because it's sort of like one and the same thing. Okay, but now in the case of the cat, remember I was very explicit that I need you to use the set and reset because I needed to test whether you're able to apply the set and reset instruction. So if you use it in this case as well, I have no problem with that. It is still fine. Instead of this large, it's still okay. And don't speak as though this is this is in the exams. We are solving what is in the tutorial. But anyway, if I were to ask it, then I wouldn't mind if you decided to use a set and reset instruction instead. And please remember, I told you again that the question doesn't specify exactly what latching we need to use. So that's why, because you are the designer, you are at liberty to choose that which you are comfortable with. It's just like writing a programming language. Okay, the idea is to solve the problem. So somebody can decide to go route A, somebody decides to go route B, somebody decides to write a function within a function, somebody decides he's not going to use functions, somebody is going to use an if loop, somebody is going to use a for loop, So it depends on how you approach your problem and solve it. As long as it works, I have no problem. That's why I told you it's very difficult for me to have a marking scheme for questions like this, because there can be so many variants of the solution and all would be correct. So I would not penalize you if you use a different technique, as long as it still makes sense and it still solves the problem. I will not penalize you. Sawa. All right. Okay, so I think we need to do the last question. Then I give you a few briefs, and then we can conclude. This question, I've seen it also in the exam papers as well. I'm saying I've seen it, but I think I've said it before. It says a single open tank that is shown below. These are just typical tank. You have an inlet, so there's a level high switch. You have an outlet, a level low switch. This goes all the way to even giving you the address systems for your contacts, for the inputs and the output. So the tank is such that you have a level low switch. So this simply is a typical question where you can actually see that. Okay, let's read it so that I'm not making up my own things. When the level reaches level low, the outlet flow is blocked and the inlet flow is allowed until the high level is achieved. And when the level high is detected, the outlet flow is allowed and an inlet flow is blocked. So you have to draw a PLC program for this. Yeah, makes sense, because this is like for controlling the levels of the water, ensuring that it doesn't overflow and ensuring that you don't pump out water when the level is way low. So there's a level low switch. There must be a sensor there, so that when the level reaches goes below the level low, then now there's no more outlet. The outlet valve is closed and the inlet valve is allowed to provide more liquid or water, whichever it is. When the level high switch, that one is for when the level is above the level high switch, then it's supposed to close the inlet, meaning the inlet should be blocked now, and then the outlet is allowed to open so that the fluid can now flow out. Okay, yeah, it's a typical question. It makes sense as well, and you have to just identify the inputs and the outputs, and I think it's just a simple problem you can solve. I don't have enough space here, so I'm going to wrap this off because I'm using the same. Let me wrap this off. So that we do this together. Okay, let me list first of all, I think we can list them here. We have the inputs. They're actually on the diagram. They're the switches. So you have the level high switch. Let me just call them level high switch. It's called I1-0. Okay. There's the level low switch, I1/1. What's another? Oh, this even tells you, because it's an input, so there are outputs as well. And it's just put here. There's the inlet valve. And it's actually written there as output 2-0. Then there's an outlet valve. And it is output 2/1. I think I specified this for you, for the students, so that it's easy for me to mark, because everybody would be using the same notation, and so it's easy to follow, rather than leaving everyone to do their own thing. Anyway, those are the ones I can see here. No, but this thing has to start, and that it has to be stopped. Let me see. When the level reaches a level low, okay. Yeah, but then you must have a start button or a stop button to start and stop the whole operation. So clearly, you need a start button and you need a stop button. And you can decide to provide maybe I1-2, I1-3, something like that. So that now you have a way to start and stop the whole system from working. But then the automation aspect is when now the level high switch and the level low switches are now, you can have sensors there detecting, and then they can either open and close the valves automatically. Okay, so I don't know. Let's see if we can solve this problem. Now, I think the usual thing is usually to sort of, once you have listed the inputs and the outputs, you have to make sense of, you have to rationalize how the whole thing is actually supposed to work. Because unless you have a full picture of how the whole setup needs to work, then you might miss something in your ladder diagram. So you can't start drawing a ladder diagram just because you have inputs and outputs. You have to sort of like envision how the whole thing needs to operate, because that's basically the design element. That's the creativity part. The rest are just conditions. These are parameters that are provided, but your creativity comes in sort of like figuring out how the whole setup needs to work. So for example, now we know we need to detect high and low levels of the liquid in the tank. So we have level switches for that. So the two level switches will now either affect the inlet and the outlet. Okay, so that when there's a high level, we block the inlet, we allow the outlet. When we reach the low level, then now we block the outlet and we allow the inlet. Okay. So those ones can usually you can automate the whole process, but just need to think around it. Now what of course this one is like now these two that I've included here is just like the control. Let me call it the master, because it's the one that either starts the whole operation or stops the whole operation. Just like you can leave traffic lights to work on their own, but you can have a switch to stop the whole operation when you want to do maintenance or troubleshooting or whatever it is. And then you can have another switch to just start or stop the whole operation. So that's like a master switch. So that has to be included in the system as well. Okay. Now, again, we expect that when I start, I don't want to start and then the water starts flowing and then I stop. So it means latching is important here as well, so that when you press the start button, the thing can work on its own up until the time you press the stop button. Yeah, so again, that's important to remember that you expect that the control valve here would be latched so that you have a continuous fill or emptying, because the process has to be automated. You can't be there to open the valves and close the valves. That's a manual way of doing it. So all I have to do is press a start button or press a stop button. When I press a start button, then I expect an automatic manual filling of the tank and emptying of the tank, filling of the tank and emptying on the tank, meaning that I'll have some pistons connected to the valve. So those pistons are the ones that will be responsible for either fully opening the valve or fully closing the valve, both for the inlet and the outlet. Okay. Now this is just trying to think through everything so that when we start drawing the ladder diagram, we don't forget any aspect that could prove crucial in the entire operation. Okay. Now, we know that now we have a master that now will start and stop the entire process. But the process itself should be automated. Once started, it should work just on its own. Okay. So now, having known that, then now we can think about the ladder diagram. Remember, latching is key because that's going to be the one that allows us to control the entire operation without having to press the button and hold on to that button. Now, the other thing that I think it's critical here is we must remember that there are two main operations here. There's the operation that when the level gets to a high, so that now we block inlet and allow the outlet. There's the operation that when the level goes low, then now we have to block the outlet and allow the inlet. But then there's also the operation of based on the switch, the start button, the master. The master has to control both cases. The reason is this, remember, this is an automated system. But for whatever reason, I can decide, because remember, when I press the start button, we haven't drawn the ladder diagram, we're just having a full picture. When you press a start button, and of course it latches, okay, the output latches, and so you're expecting that the whole process can operate even in your absence. However, we have to remember that in this case, either the first thing that will start happening is, maybe let's say we are beginning when the tank is empty. So the first state is the tank is empty. So when I press the start button, of course, it means the sensor will detect that the level is way low because the tank is empty. So what it will do, it will first of all block the outlet and then allow the inlet so that water starts flowing into the tank. Remember, now this process has been automated. It's working on its own. So the water level rises until it gets to the level high switch. Once it gets to this level high switch, okay, we can have a condition where, because we've had the high level, then now we block the inlet. Remember, I told you can connect it with a piston valve to open and close. And then now, once you block the inlet, because now you don't need more liquid flowing in or more water, then now you can allow water to get out, or that fluid or liquid to get out. And the moment you've blocked this, it means that now water will start reducing, and then it goes back down. And when it gets to a low level again, the next condition is that this has to be blocked now, and then now you have to open this so that again water starts flowing in there, so then we start filling. So then the whole process just repeats on its own. However, let's be realistic. We cannot assume that the conditions will just work so perfectly that whenever I go to my master and press a stop, for example, remember we had pressed the start button. So when I go and press the stop, it will be either in this condition or in this condition. That's not true. In reality, for whatever reason, I can decide to press a stop button, and maybe I press the stop button when the liquid level was somewhere here. So therefore, it means that it's neither a high level, neither is it a low level. So what happens in this case? Because in this case, are we supposed to be, in this case, are we supposed to be emptying or are we supposed to be filling? Okay, so please remember that in our design we have to remember that there is a condition where we can have the level that was maybe, I'm not saying exactly in between, but the water level could be at any level of the tank. It doesn't have to be at exactly the low level, because when it's at the low level, we know what needs to happen. The outlet is blocked, the inlet is allowed. Or it cannot always just be at the high level. It could be somewhere in between. So we have to take into consideration that point. So what that means is, for the inlet valve, for example, to be opened, we must know the low level switch will determine when the inlet valve is open, because the moment we detect that the water level is low, we block the outlet and then we allow the inlet. But again, if the water level was in between, then the level switches don't know, because the level switches are only at this position and at this position. So in between, they don't know. So it is me manually who I can start the whole process again, so that the water starts flowing in. So there is the level low switch and the level high switch. These ones are automatic, meaning they're supposed to operate automatically on their own. But in certain cases, we have to face it that we must probably have to start and stop and start the manual filling. So we'll get to that when we are drawing the ladder diagram, so that we consider all the conditions. But what we also have to remember, so that I don't forget, what we also have to remember is that you cannot have the low level switch and the high level switch in the same position. What do I mean? I mean, when the high level switch is activated, then the low level switch has to be in the opposite state. And when the level low switch is activated, then the level high switch itself has to be in the opposite state, because both of them cannot be in the same state. We can't detect a high level of water and a low level of water at the same time. They have got to be in the two opposite ends. So if one is a logic high, the other one is a logic low. If one is a logic 1, the other one is a logic 0. That's because you're either in the process of filling the tank, or you're in the process of emptying the tank. So you can't be filling and emptying at the same time. At least this design doesn't allow you to do that. So you can't fill. Of course, I know there are applications where you can fill and empty at the same time, but in this case, the instructions were clear that when one level is reached, the outlet flow is blocked and the inlet is allowed. And then the other case also applies. Another level is detected, the outlet now is blocked, and the inlet is allowed, and so on. So we have to know that here we only have two scenarios. Either you're filling the tank or you're emptying the tank. You can't be doing both at the same time. So it means that the state of these two switches have to be in the opposite direction. They have to have opposite states. Okay, let's start with the basic one. Let us latch our circuit. Usually that's rung 1. That's now rule of thumb. We know the first rung, we need to latch our circuit. And latching our circuit is simple, because a latch is typically your start button. Now, I'm not drawing the physical devices, ladies and gentlemen, because in this case now, you know the physical devices, okay? So let's say in this case that we are not drawing physical devices. So here now we are PLC programmers. Let's draw this so that you know what I mean. We can readjust by drawing the physical devices like we did in the previous case. I think it's rubbed off, but let's forget about that, so that we just have the ladder diagram itself. to illustrate, but you know how engineers think, and you know that includes the physical devices. But in this case, for ease of illustration, let's just, so this is the start button. So let's have the stop button, and we know the stop button should be, so this is the stop button. Now, if I were to draw the normally closed contact for the stop button here, then I'll have to make this a normally open contact. Now you know that anyway. So, but I'm just drawing this so that we are able to move and on. And of course, now you've got your, this is the one that controls the entire system. So we can call it your master, because it's like the switch that controls the, decide when we are starting to fill or when we are starting to empty. Okay, we can either start to fill or we can start to empty. And because we are latching this system so that it works without our intervention every time, then we can latch it like this. So this is the master. So I've basically latched the master switch so that it can work without any intervention up until we press the stop button ourselves. Okay. So now we know that that switch now is the one that will either now do the filling and or do the emptying of the fluid. Okay. Now let's control the outlet valve. Let's control the outlet valve. So let's say we have when the level high is detected. So we were saying, let's say that we started with an empty tank. So somebody has gone and pressed the start button, and of course the water level starts filling up. I mean the tank starts filling up, and then now we detect a high level switch. So what happens when we detect a high level switch? So it means that the switch that would be active there is this guy. I keep confusing it, but it's let's call it level high switch. So level high switch, let's abbreviate it to LHS, level high switch. So we definitely know that that would depend on your master. This is rang number, whatever. So this is your master. Let me write it down here. Okay, because remember this first one is just for the master start stop. This guy is just master start stop push button. Okay, so just to latch that, the latching a coil in the master start stop button. So now we have conditions that we are now considering when high level is detected. So let's say the high level is detected. So what do we do when the high level is detected? So when the high level is detected, you have the high level switch that would have to be energized. Okay. So therefore, we have to put the high level switch. We are calling it LHS. I think it's given here even I1-0, something like that. Okay, it doesn't look too good there, the way I've written it there. Let me put the LSH down, put it here, LHS, and here it is I1-0. Okay. Anyway, I don't need to put the addressing. At least I've just shown you what is happening here. So remember, what are the conditions? Because remember, what needs to happen when the level high is reached? When the level high is reached, we know that what should happen is that the inlet should be blocked and then the outlet should be allowed. So the outlet valve should be allowed and the inlet should be blocked. So remember, we are trying to see what will activate the outlet valve. So what will activate? So our output here is for the outlet valve. So for you to energize or open the outlet valve, we need, of course, the master switch. So the switch, we know whether it's a start or stop, whatever. We have the low, the level high switch, and during that condition, to make sure that we don't have any confusion with the level low switch, this is the level low switch, this guy, level low switch, LLS. So we know that the level low switch should never be active at this point. So we can have it there because it's an AND. So this is level low switch, just to ensure that we are sure that when one condition is activated, the other one cannot work. So the level low switch here is not operational. So the condition that will activate the outlet valve, that will allow the outlet valve to work, is when we have the low, sorry, not low, but level high switch, LHS, the level high switch. I think if you think about it, that condition as well should work on its own. What do I mean? What I mean is this. What happens, because we had said that the outlet valve, let's say we've reached the level high condition that we were saying, then we expect that the water, or in this case, let's just talk about water would start flowing out because the outlet valve will be open, and then the inlet valve, we know that in that case has been closed. Okay, so water level starts flowing out. So it is this, we have activated this output 2-1. That is the one that has been activated. But remember, when it's activated, the water level will start reducing up to the level low. But again, when we get to the level low, we would be expecting that certain conditions would be met, and then the output will now be closed, and then the input would be allowed. This inlet will be allowed. And even after that, the system should go back again with filling the tank with water, and then we go back to the level high switch again. So automatically that system should work without any intervention, meaning we must also latch this condition so that it is working without intervention. Otherwise, if we don't latch it, then the water level, meaning once the water level would be full, the tank is full, we will then empty it, and when it is empty, then the system stops. So we'll have to again intervene manually. And we don't want that. We want the emptying and the filling to be working automatically. So therefore, each condition, even this one, should be latched. Remember, this is the input. The level high switch is the input in this case. This guy is just a master because it's the master switch. So we must make this an outlet valve. We must latch this condition as well. Okay, so that it is also working without our intervention. Okay, it's also working up until we, now notice the condition to stop this, the condition to stop the outlet valve is this guy here, is this guy. That's what we mean. That what we are saying is that the process will be emptying the tank, because now the outlet valve is open. The process will be emptying the tank until a condition is met. That's the latch essentially. So we will be emptying the tank until we reach the what? The low level switch. So that's why we have this low level switch here, because it is the condition that will now stop the outlet from working. So we have latched into emptying the tank through the outlet valve until the level low switch is activated. Just like we do with the start-stop push button, the latch in the first rung. That's the same thing in the second rung. in this case, that we are trying to empty this tank. We were saying, we are assuming in this case that we were beginning with a high level of water. So we were emptying the tank. We were emptying the tank until the low level condition is reached, or the low level switch is activated. That is why we have that latch there. So that's important also to remember, because if we don't put that latch there, then it means that the emptying will be happening throughout, and then filling also wants to start happening throughout, but it is controlled. We fill, after we fill, we empty. When we are filling, we are not emptying. So it means that one condition will be latched on to until another condition has been met. So like in this case, we are latching into the emptying condition. So emptying is what we are doing here. We are emptying the tank until we activate, until, let me just say, until we reach low level. Okay? Until we reach the low level. That's basically it. Because if I don't latch, then the emptying will just continue throughout. And then when we reach low level, then the water would start filling again throughout without any stops. But here we must stop. When one condition is working, the other one needs to stop. So when we are emptying, we must not be filling. Okay? That's why we put that latch there. Now, let's look at the last one, because there were only those conditions. So we've emptied the tank up until we have reached the low level. So again, just like we've done with the first rank, the master is the first condition, because it would depend. Will you have pressed the start button at that point, or will it be the stop position? Because here, if it is stop, the whole thing will not work. So here in this case, you needed to have had a start. So the same thing here. So the master is important, because it's what dictates the whole thing, whether you have it in the start position or the stop position. Okay, so the master, and then let us consider the next one. In this case now, the other level low switch is the one that now is important in this case. It is I1/1. It is the level low switch. Okay, and remember, if we were to latch onto this condition as well, then now the other one must not be working, the level high switch. And this one is now for the inlet valve, because remember, this one is the one that now activates water to start filling, because we've reached the low level. So we need to activate the inlet valve. We are activating the inlet valve, and we are latching that inlet valve. So we are latching the inlet valve, so that we know that that inlet valve will only be allowed to open to fill the tank up until we reach the high level position again. That's why we have it here, that we latch into, this is filling the tank. This is now filling the tank. We latch into filling the tank until we reach high level. So we fill the tank until we activate the level high switch. That's why we are having that latch there. Here we were emptying the tank until we activate the low level switch, because that's the condition that gets the latch out, with that unlatches. That's the condition that unlatches. So this is now the condition that unlatches. The low, the level high switch is the one that now unlatches in rank number 3. Okay. So again, we know that that condition unlatches there. So therefore, we know that we are sure that when we are emptying our tank, there's no filling that is involved. The inlet valve is not involved. And when we are filling our tank, the outlet valve is not involved. So when we are emptying, the inlet is not involved. When When we are filling, the outlet is not involved. Okay? So basically, this is how it is. However, I remember I mentioned while we were thinking or envisioning the whole process, we said that this process is too ideal, that we are only operating between two conditions of the level high and the level low, when we know that in reality, the system might be started when the tank is partially filled. So that means at that position, the tank is neither at level high, nor is it at level low. So in this case, like the case I was telling you is this case, where this switch here is not detected, and this switch here is not detected, because the levels have not been reached. So in that case, we must also incorporate that condition in the ladder diagram. Okay? Because if this condition is not met, then it means, therefore, that the inlet valve is closed. Okay? The outlet valve is closed, because we are in between. Remember, the idea was we reach the LHS level high. What happens at level high? We know that at level high, we close inlet, we allow the outlet. At level low, we know by the conditions that were given that level low, we now close the outlet and allow the inlet. But now, medium level, what do we do with the medium level? Because at medium level, both the inlet and outlet would be closed. In that condition, if you were to start this system when the water level is at the medium level, then both the inlet and outlet is closed. So what happens? So this is where in your own design, somebody can say that in my design, if neither the level high switch is activated nor the level low switch is activated, I can decide that if I were to start the whole process in between, somebody can decide that in my design, when we are at medium level or in between, then empty the tank first. Or when we are at medium level, fill the tank first. Okay? So otherwise, there's going to be an error. So you have to decide, which one are you going to use? Are you going to say that if this is not detected and this is not detected, what are you going to do? Are you going to empty your tank, or you are going to fill your tank? Now, to be safe, this is the best one. To be safe, would you rather start filling the tank or emptying the tank? So you can have a condition. So like in this condition, you can say that if this condition is not met and this condition, remember the level high is not met and the level low is not met. So you know that your water level is somewhere in between. So you can decide that, okay, if you remember how we began, we were beginning as though our tank was empty. So we started by filling the tank. So you can decide that in my design, if in this case, we can start filling the tank when the level is neither high nor low, meaning you want to fill it completely before you start emptying. Another person might decide in their design, when the high level and the low level are not met, you empty the tank first before we start filling. Now, if you decide to start by filling your tank first before you continue, that is when neither conditions are met, then you'll have to include a start here. You have to include a start there. And let me explain this, because it's a very simple thing to understand, but at first it might confuse you. So the reason why we are connecting all this, branching out all this, is because we know that this condition or this condition, or this condition is enough for me to engage the inlet valve. So the reason why I put the start here is for cases where the system had been stopped when the water level was neither high nor low. So if the water level was neither high nor low, and then now I switch on my whole process, if I switch on the whole process, then now I can, meaning that I start the process, then now I can start by first filling the water. On the other hand, if somebody decided that, Mimi, I want my water level to empty completely fast before I start filling, then you would be forced to include a start here in the second rank. You'll have to include a start here, because if you put a start here now, it means that if the water level was in between, then now you start the process. What happens is now you'll start by first emptying whatever little was in there before you start filling up again. So again, that depends on you. But if you don't put anything here, there's going to be an error, because the system will only be working perfectly when the water level is at this point. I don't want this to be so untidy. The system would be working at only these points, so that when you switch on, it's either expecting to be at this point, then it starts emptying, or it's expecting to be at this point and then it starts filling. But now, if the water level in real life was in between, and then you engage your system, it will give you an error, because now this has not been detected and this has not been detected. So it doesn't know what to do. So it is you, the designer, who needs to decide that if neither level is detected, then just open the inlet valve so that it fills up. And when it fills up, this level high will be activated later. Or you can decide that if neither the level high or level low is detected, then just open the outlet valve. So you start emptying whatever little was in there until the level low is detected. So in that case, you'll now have to engage. Either you connect your start at rank 3 or at rank 2. If you connect it at rank 2, then whatever was in the tank will first be emptied before the process goes on. Or whatever, if you connect it to rank 3, then now whatever is in the tank will be filled to the high level first before you start emptying. So I hope that is clear. That's why I told you again, with design, it's very difficult to just have a one solution for all the problems. People can think differently. For me, it's just to make sure that you don't leave this state uncatered for. The state where the tank is neither empty nor full. So that condition has to be taken care of. And the way you take care of it is what I have told you. You either just instruct the outlet valve to open, meaning you'll be emptying, or you can instruct the inlet valve to open, which means you will be filling the tank first before the process now continues as was prescribed in the conditions. So that is what I wanted to tell you regarding this. Kama kuna swali, uliza. Let me check if we have questions in the chat. Yes, I see a hand up, which is Eric. Go ahead and ask.
Yes, I just wanted to ask about the two switches, the high level switch and the low level switch. Whether there's physical switches that will be controlled, or they will be basically controlled by a sensor like a ultrasonic sensor, which will sense the level of water. Then we'll be sending a signal to the low level switch or a high level switch, depending on the water level. So that way will be remove the redundancy of using latching in the low level and also the high level, and as well as it will also remove the issue of whether the water will be in the mid level. Yeah, because if you just have the physical sensors, that's where we'll have that particular situations. probably have to launch the input, the input devices or the input instruction, and that is why I'm saying like we'll be just using a physical sensor. Let's say like the ultrasonic sensors will be just be telling us whether water will be at high level and low level, and we'll be just sending the signal to the high level switch and the low level switch, depending on the level of the water. Yeah.
Yeah, thank you for your good question. Yes, this assumes the rudimentary, just the physical switches. That's why we're actually doing the latching, because we're assuming that if we will have physical sensors acting as the level high switch and the level low switch. Because remember, we are trying to see how we can actually implement this in real life, and so you'll definitely have to install a sensor for the high level and another one for the low level. And those sensors would now be responsible again for, remember, even the valve inlet and outlet, we are not opening them manually and we are opening them through a piston. So you have to connect some sort of like a piston valve, or I don't know how to call it. How do we call that? You have to connect a piston valve really to either. These are not those valves where you rotate and rotate. It's just a valve that either stretches. I wish if you've gone to places like how do we call those places? Kipevu 1 or Kipevu 2, you see the valves that they have are not operated manually. So there's sort of like a piston that either opens the whole valve or closes it. So in a nutshell, yes, this design assumes that we have physical switches here, and so or physical sensors for switches, and we have actual acting piston valves to either open the inlet or close the inlet, and also the same for the outlet. So in those conditions, like you say, I agree with you, we'll be forced to do the latching, and then we'll also be forced to consider conditions where the water level is just in between. Otherwise, you could have a design where you have to eliminate the issues of latching, and you have to eliminate the issues of trying to see at what level you have. You could incorporate, like you say, other switches that are not physical, so that now, for example, if I installed I don't know, if we had a sensor that is able to scan through the entire length, or in this case the entire height of the tank, so it sends a beam through the entire length of the tank, and then now you can detect at what level the water is. Then you would not need to include these cases where you have to consider whether the water level is in between, because you'll know exactly the level of water at that point. But now it's a very refined design. Okay, what we are trying to do here is just a very basic design that you can implement even at home, and you can use it to learn, but later you can improve on your design and make changes to some of these inputs and outputs, so that the issue is not really detecting water levels at only 2 points. This one you can see from the instructions that were given that we can only detect water at 2 points, at a point level high or at a point level low. That's what the instruction is. But you see, if you are to do a proper design, then you could include your design in such a way that you can be able to detect the water level at any point in between the height of the tank, and then you can decide what actions to take based on that level. So yes, that would save you issues of latching. It would also save you issues of considering where the level of water is. But because our design here specifically indicates that you can only detect at point level high and point level low, then you have to take into consideration the conditions that we have taken. But I agree with you, you can make your design much better to reduce some of these excesses of having to latch your systems, and also to add in the start for in between conditions. So in this case, you have to just go the route that we've been asked to, but I know you can refine your system. And again, refining your system means it optimizes the whole operation. The scan cycle, the scan time will be reduced. And so if that is reduced, then your system works more efficiently. But in our case here, it's like this is, let me say semi-automated. It's not fully automated. It's sort of like semi-automated. Sawa, Eric?
Yeah, thank you, sir.
All right. Kuna mtu mwingine ako na swali? Let me check because I need to conclude, guys. We don't have to go all the way to 10 o'clock. Remember, I'm borrowing your time. Okay, I've seen questions in the chat. From Gathecha Nicholas, could we negate the output of the outlet valve and use it together with the master as the input conditions to the inlet valve, such that if one valve is closed, the other is open? So the Gathecha is asking if we could decide that we take this, we negate the output of the outlet valve and use it, of course, with the master as input conditions for the inlet valve. So I don't know if anyone could respond to that. Is it? You can also see the question is asked in the chat. I just need to seek your opinion on this. Is it proper that because we know that when the outlet valve is working, the inlet valve should not be working and vice versa. So should we take, for example, the outlet valve, negate that output, use it together with the master at the input as the input conditions for the inlet valve? Kama kuna mtu anaweza jibu hiyo, nitashukuru. Because that ensures that if one valve is open, the other one is closed. Any thoughts around this? Is it possible to negate? Yeah?
I have a question. When you said the master, is it the master coil?
Remember, the master coil, of course, the master is a coil here because it's an output. But remember, the output that we are talking about here is basically the switch, the master switch. This output here is a switch, actually, so that you don't have to keep pressing start, stop, start, stop. So when you press start, the whole system will be operating on its own, so that even when I release my hands from the start button, the system continues working. So this master is basically a switch, but we've borrowed it from the rung 1. So it was the output in rung 1, but it becomes the input of every subsequent rung, because we were just latching it in rung 1 so that it's used consistently in all the conditions that are involved. So it is actually a switch.
Okay, when you say start, does it start the process or does it start the inlet?
Okay. When look at the ladder diagram, Stephen, if you check the ladder diagram correctly and the conditions that we had said, usually to help you understand this, you need to write a Boolean logic expression. That sort of is closer to English, and then it helps us understand this. Because now you see here, we'll be having if there's a master switch involved, master switch. So the master switch can either be off or on, okay? And the input, the level high switch, or of course the outlet valve. Now this one is for latching, we know that. And of course the condition for the low level switch. Then you get the output. So notice this, Stephen. The master is not starting the outlet valve on its own. There are other conditions that must be met. That's why you have to take the condition of the master switch, combine it with the condition of the outlet valve, and or the condition of the input 1-0, the input itself, and also consider the level low switch condition. Then you can now either open or close the valve. So the switch doesn't directly open the outlet valve. These other conditions must be met as well. Because if either one of them, except the ones that are under OR, if either one path, this or this path, okay, if either one of them is 0, then the outlet valve is 0. It will not open. So I hope you get that. So the master really is like a switch for the entire system, but it is not the one that's opening the valve on its own. It is one of the conditions that must be considered. So the switch is for power. Sijui kama tunaelewana?
Yeah, it's okay.
Yeah. So the master is not responsible to open. Otherwise, we would connect the master straight to the valve. But you remember, we have to go through the other switches as well. We have to consider the high level switch, or the outlet valve itself, or the low level switch. We have to consider all the switches before we get to the outlet. And the same thing happens with the inlet valve. They don't operate on their own. Yeah, so back to Nicholas Kamunya's question, where we was asking if we could negate the output of the outlet valve and then use it to control the inlet valve. I don't know, Nicholas. To be honest, maybe I try simulating that and see if it works. Because if I say no, it might. Yeah.
I think it is correct, because like when you use the negated value of the inlet valve to be one of the input values to control like when you use the negated output value as the input to control the inlet valve, I think it's correct. Like when I did simulate it was also correct, and also the example I did do there was also correct. Yeah, because it will automatically control the opening of the inlet valve when it is open on the other side. Yeah.
Okay, thank you, Gola, for that. Now, please listen to this carefully. I am not refuting whatever you have decided. That works. But in engineering, we say logically it works. Now, I think somebody asked me this question on an email and I responded. Maybe it's Ismail. Remember, guys, we can tweak this ladder diagram to work logically, but practically things might be different. Now, because you guys are being baked to work in the industry, or at least to do some work for yourself, but you'll be in a practical world, I'll have to be very candid with you guys. Yes, logically, I can tweak the outlet valve, negate it, and use it together with the master as the input of the inlet valve, and it will work logically. Now, practically, issues arise. When you connect this now in a practical scenario, one of the issues that we often forget about, but we realize that we can never run away from, is issues to do with troubleshooting. In fact, in the industry, because PLCs are very reliable systems, one of the biggest challenges we face in working the system is when we have a problem. Troubleshooting becomes one of the biggest headaches that can take you days. You know how the system works, the ladder diagram is, you see, but now when an issue arises, then troubleshooting becomes the problem. Now, when you do that, when you negate the output of the outlet valve, for example, and now you use it together with the inlet valve, you logically will have the system working. Okay? But the problem is, and please don't remember that your system will not only have two rungs. Your system can have as many as 20, 30, 40 rungs. Okay? Whenever a problem occurs in a run, it becomes very, very difficult to figure out where the problem is, what we call debugging, okay, in the conventional programming languages that we use. Debugging becomes a serious issue. Why? Because you've borrowed certain conditions from the previous rung and you've used them in the subsequent rung, meaning you have layers of challenges to run through to figure out where the problem is. So yes, your system might operate well, but the problem is you've made it so complex that now whenever an issue arises, it becomes very difficult for you to figure out exactly where the problem is. Now, we usually say when you're doing your designing as an engineer, it is always important to have a very lean ladder diagram, meaning it's only uh, taking what is necessary. You don't put any redundancies and stuff like that. But again, you also have to remember that that would involve borrowing conditions from the previous rung and using them in subsequent rungs. The challenge with that is usually when now a fault occurs, figuring out where the problem is becomes a challenge. Unlike in this case, I could run one rung at a time and figure out, okay, this is fine. Then I go to the second rung and run it independently to see how it works. But now, if I had borrowed conditions of rank 2, put them in rank 3, conditions of rank 3, put them in rank 4, and so on, then it becomes a very tedious process. I'm not saying it doesn't work. I am saying it may work, probably will work. But your challenge is always in debugging your system or having to troubleshoot to figure out where a challenge is. So always remember this, because you're going out there and you'll be probably required to make decisions. You will have to remember what works logically, but what works practically. So you must have a balance between what logically works on paper and what works practically on the ground. Because if you don't, then you'll run into problems, and then now it makes your work a living hell. And you'll be like, but we did this and it was working. But now in reality, you're having a few issues. So always just remember that try and avoid over complicating or over borrowing from previous ranks, because then it might give you issues. Unless you're so good that even in troubleshooting, you can remember each of those systems the way they were, and you can quickly troubleshoot each line, remembering exactly the states of the previous conditions. But that becomes a very difficult thing, especially if your ladder diagram is 100 rungs. Human beings don't really have the capacity to remember conditions of 100 rungs. If you're dealing with 2 rungs like this, that one you can do, you can remember. So, Stephen, your case would really work, especially in this case, 2 rungs. Troubleshooting cannot be a problem for 2, 3 rungs. But now, when you're dealing with tens or hundreds of rungs, then that is where the rubber meets the road. So, yes, always remember what logically works and what practically works. That's very important. And that's the same thing that I told you regarding the programmer's view and the engineer's view. The engineer is a practical guy. The programmer is simply a software guy. And in software, you can tweak things to work. But now in practice, when you connect the physical devices, things tend to change a little bit. So that's important. Anyway, guys, I don't know if there's any other question. Okay, I need to conclude because I also have to prepare for the next class at 10. I just want to state this. I don't know when you're doing the exams. I can't remember, but I'll check. However, typically I set 4 questions for your exams. Of course, question 1 has the highest marks, which is 30, and it's compulsory. So you'll have to do question 1, and then you pick the other questions as well. 2 other questions, because the other 2 questions are only 20 marks each. Now, question 1 usually covers everything, but those 2-mark questions, 3-mark questions, just a little bit here and a little bit there to test your knowledge on everything that we have done, right from definitions of PLCs, Ukoju, all the way to what were they called? Program control instructions. Okay, just a little bit of the describe, the list, the explain, just those simple marks of just knowing simple things. Okay, but now the other questions, question 2, 3, and 4, require you to go into design mode, because now we are testing if you're able to come up with your own designs. So that is where you'll be drawing a lot of PLC ladder diagrams. Okay. You might be asked to state a few things in between, but the main core of the rest of the questions, the 20-mark questions, are always design questions. So they are not so detailed. Okay. They're always just design questions. And those questions carry marks. A lot of them carry marks beyond 5 all the way to 10 marks. So those are simply design questions. And so I ask that you cover everything that we have done, because a little bit of each will be tested in your question 1, which is compulsory. So you can't escape and say, I'm not doing this topic, or I'm not doing this topic. You have to cover at least all the topics to be comfortable in solving the problems in question 1. And when I say all the topics, I mean all the topics that we have done in class. I don't ask things I have not taught. Okay, I'm only asking you things that we have done in class. So I am sure that everything that you see on that paper is something that we have met in class, talked about it, either in an online class or a physical class. So please take your time to have a proper revision. The idea, like I told you before, I would love that you pass this course. That's fine. But my main concern is that when you go to the industry, I need you to hone your proper knowledge around PLCs, so that beyond the classroom, you're still capable of solving real industrial problems. That's where my desire is. The exams is just a by the way. It's a 2-hour thing. But now in the industry, you'll have a lifetime to solve issues. So that's where you really have to focus. But anyway, as I said, make sure you have your knowledge around everything regarding PLCs, right from the beginning all the way to the program control instructions. And then you should be fine. You should be fine. Make sure, again, you go through the tutorial. I think we've covered everything in the tutorial. Go through that as well, just again to boost your confidence in how questions are approached and solved. Very, very important. And then you should be fine. Again, you have the liberty to only do 3 questions out of 4, with the first one being compulsory. So it's a doable thing. It's not so complex. So kama kuna swali ingine mnaweza uliza, kama hakuna, then we'll end our class here. This is the time you have to ask me any question, because I don't think, unless you're planning to come and repeat this unit, I don't think we'll meet again in this setup where we are doing industrial automation in class. This is our last class. The whole of next week is for you to do your revisions, and then you can comfortably cover the exams in the following week. Kuna swali ingine on anything we've covered so far from the beginning, so that we conclude our class? All right. I hope you guys would do well. I think I will pop in the class during your exams just to make sure.
Hello.
Yes? Marigu?
It's not a question, but just a compliment. It has been nice having you as our lecturer. It has been
Please
a nice session.
move closer to your microphone, Marigo. I can't hear you properly.
I mean, not really a question.
Yeah.
I think we are contented enough. Just a compliment. It has been nice having you as our lecturer, and the unit has been covered. Okay, we are grateful.
Oh, thank you so much, Moses. I don't know whether you're speaking for yourself or you're speaking for the entire class. But anyway, even now, between now and sorry.
For the class, another one from the class. Hii ni mtihani ya mwisho, usituangushe.
What do you mean nisiwangushe? That power is not with me, Moses. Kujiangusha ni wewe mwenyewe unaamua kama unataka kujiangusha ama ujiangushe. Yes, so if you actually did my CAT and you do your revisions, we have done revisions together as well, and you study the notes that I provided you with, I don't think you should have a problem. Unless somebody is planning to do. That's why I have to pop into the class and your exams and make sure that the exam you're sitting is the one I set, okay? Because mnaweza sema mimi nimewaangusha na kuna mtu mwingine kwa examination department ndiye amewaangusha. But anyway, for me, you should be okay with the exam because it's nothing strange, it's nothing new. I don't like surprises myself, so you will not be surprised with the paper. But please, I am glad that quite a number of you have also demonstrated an interest and willingness to learn more. I usually enjoy that because it's a learning experience for both me and you as well. So thank you guys. You've been a wonderful group. I am sure we are not at the end yet. So let's hope that between now and the end, which is in a few weeks, you'll be able to successfully get over to the shore, just keep the fire burning, just keep at it. Don't give up. This is your last lap. The last lap is usually very anxious or nervous time, but if you keep your nerves calm, then you should be fine. Okay, I know there are a few cases, one or two, that usually have issues, but those ones again, we can never do anything about it, at least. But for you guys, I wish you all the best. I hope you will not disappoint me as well in the exams. So all the best in what you do. Have a good day ahead. If you have any questions between now and the exam day, I'm still available on email or through your class rep. And so you can consult with me anytime. All right. Thank you guys and have a good day. Goodbye.